Welcome back. Now we're still going over different examples of systems that demonstrate simple harmonic motion. So let's take a look at another example. Let's take a look at a mass that is bobbing up and down in a fluid. So let's just say that we have our nice fluid and we're going to just put a little block in it. The block is going to be partially submerged. So here's our fluid. And we're going to say that the fluid, it could be water, it could be who knows what, but it has a density given by rho F. Now let's just say that the mass has the block has a mass m, and right now it's at this nice equilibrium where it's partially submerged. So since it's at equilibrium, all the forces that are in play right now are balanced out, and the only two forces are the force of gravity pulling it down, and a buoyancy force pushing the mass up. Well, we know what the force of gravity is for a block of mass m. That's just going to be mg. Now, the buoyancy force, if you recall, that's going to be equal to the weight of the water displaced by the mass that's partially submerged. So right now, like if we didn't have a mass, there would be water in this area right here. But by putting the mass in, we've pushed that water away and we've given almost like an extra pressure or an extra force, the buoyancy force, which is going to be equal to, just say, the mass of the fluid displaced times gravity. Now, we don't actually know the actual mass, but we know the density, let's say, which means we can rewrite this as the density of the fluid times the volume of the fluid displaced times gravity. Now, we know that the volume of the fluid displaced is just going to be equal to this volume here, the volume of the mass that's underwater. So, let's just figure that out. Let's just say that the mass has a cross-sectional area A, and that this amount here, the length underwater, we're going to call that h. So that means that our volume that's submerged, that's going to be equal to A times h, or our total buoyancy is going to be equal to rho F A times h times gravity. And we know that it's at equilibrium, so these two forces are going to be balanced out. So we're going to get that the mass of the block times gravity is equal to rho F A H times G. So now let's see what happens if we displace it away from equilibrium. Let's just push on the mass so it submerges down a little bit. So here's our mass now. And let's just say that we're going to define like the water right here, that's going to be y is equal to 0. So now let's take a look at the forces in this case. Now, the force of gravity, that's going to be the same considering the mass of the block isn't changed. But now, since we've pushed it in more, we've displaced even more water, which means there's going to be an even greater buoyancy force. And that's going to try and restore this system back to equilibrium. So let's just say that the total amount it is displaced, if this is our original length h, is displaced an extra amount y. And we're just going to define y to be positive going down. We can define positive as going up, but we'd have to change a couple minus signs. Either or is still going to be consistent. So let's take a look at our equation of motion. We're going to take a look at the net force. That's going to be equal to the force of gravity going down, mg, minus the buoyancy force pushing up. So the buoyancy force, that's going to be equal to our rho F times g times the volume displaced. Now the volume displaced is going to now be, it's now going to be our cross-sectional area A times this new length, y plus h. And that's going to be equal to ma. So now we can distribute out this rho GA term, so we're going to get that mg minus rho f GAY minus rho f GAH is equal to m, and let's rewrite our acceleration in terms of displacement, second derivative of y with respect to time. So now, like the case with the vertical mass and spring system, we can try and simplify this up by using our equations that we got from the equilibrium condition. We found that at equilibrium, mg was equal to mg is equal to rho f a hg, which means that this term here is going to be equal to this term here. And since we're subtracting this term, that these two terms will cancel. So we're left with, let's just divide by m on both sides. We're going to get the second derivative of y with respect to time is equal to minus rho f g times the cross-sectional area divided by the mass times y. And this is of the form of our characteristic differential equation for simple harmonic motion, given that omega squared is equal to rho f GA divided by m. And that means that our mass is going to bob up and down with a period given by 2 pi divided by, or times radical m over rho f GA. Okay, so let's call it there for today and take a look at more examples in the next video.